So autoencoders try to learn a latent representation. So we have an input image, try to compress that input image into a latent representation. And the decoder, that's what the encoder is going to do. Encoder is going to learn this latent representation. How can we compress this image into a lower dimensional latent representation that contains as much information as possible in as few dimensions? What's the purpose of this latent representation? Now you can have a 2D latent representation if you can have an image that's, let's say, 256 by 256 pixels, and you could compress it into 2D representation. But is that going to be an accurate and a robust latent representation? Probably not, because you're compressing and you're probably eradicating much of the useful information. So the point of an encoder is to take that input image, to learn what the latent representation could be, and to forget all of the unnecessary information and compress it to a latent representation. And the decoder is going to take that latent representation that the encoder outputted, and it's going to try to reconstruct the original image. And then what it's going to do, it's going to try to minimize the reconstruction loss, which is pixel by pixel difference between reconstructed image and the original image. And now VAEs come into play where they say we're not going to output a single deterministic vector. We're not going to output a single deterministic vector that lives in the latent space. That's not going to be our latent representation. Instead, we're going to output a distribution in the latent space where this image could have actually originated from. Okay, so it's trying to learn the underlying distribution of where the data is coming from. And so it's going to output a mu or a mean and a standard deviation of the vectors in the latent space that way from which this image could have been generated or could have originated from. And then the decoder is then going to randomly sample from this distribution that the encoder produced, and it's going to then reconstruct the original image. And now what this allows it to do is the decoder may not select the exact perfect representation of the latent space. It may select a point or a vector that's slightly different than the exact mean or from the exact center. And so even a even if it's slightly off from the center, that should still produce an image that's close to the original image. So what this allows it's able to learn that similar points around plus points that are clustered together in a latent space should produce a similar image. So that's what it's learning. It's learning what groups of clustered points in the latent space, what types of images should they be generating. And so that allows the variational autoencoder to also generate new images that are similar to the ones that it has been trained on. And in addition to this, what we don't want to do is we don't want to just have latent vectors randomly, right? If we have latent vectors at random places, what could happen is the decoder could then randomly sample at a certain point, and that this certain point can then have no representation. We don't know how close it is to other latent vectors. So what we want to do is we want to create a latent space such that the all of the vectors in the latent space are follow the standard normal distribution. So we want the output from the encoder the distribution that it provides of the vectors, we want that to follow a standard normal distribution with mean zero, variance one. And so in addition to the reconstruction loss, we also have the KL divergence loss we're trying to minimize, which is we're trying to minimize the difference between the distribution that the encoder produces and that of a standard normal. So we want, and it's not going to be exactly a standard normal, right? It's going to approximate, it's going to be close to it. It's not going to be exactly a standard normal. We want it to be as close as possible to a standard normal to ensure a smooth latent space. Transformers, right? So transformers, we have encoder, decoder. We know GPT is decoder only, meaning it is next token prediction. And when we say next token prediction, it's only able to look at the previous tokens. It's only able to look at the previous tokens. And what it is, it's auto-regressive. So it predicts the next token, then we have the beginning of the sentence up until the token that is predicted, and all of that is then served as input. Then we do the entire self-attention mechanism again, and then we predict the next token, and then that goes back into that decoder, and then we use that as input, and we do self-attention mechanism again and produce the next token, and it's iterative self auto-regressive process when we talk about generating long sequences of data. No, transformers encoder. What is the encoder? What is the encoder? What is the step by step? So first we have an embedding. Now these embeddings are learned of what the sequence is. All right. So after tokenization, right, we split it subword tokenization. After tokenization, we have the sequence. Then we have this embedding, which gives it some meaning, right? Meaning of the words. So it depends on what embedding dimension we have. If we have let's say a five token sequence, each of them is 768 embedding dimensions, so we have 5 by 768. After this, we add in positional embedding. Positional embedding can be learned or it can be fixed. In vision transformers, it is learned, but it usually is fixed. We add this position embedding element-wise to our contextual embedding, and then this serves as input into our encoder. This serves to our encoder, and we can have multiple then encoder blocks as well, transformer blocks. And each block, and we'll go through what each encoder block is. Each encoder block consists of a self-attention mechanism, then we have, after the self-attention mechanism is done, then we add it back to the original. So we have residual, then we normalize. So then we have layer norm, then we have an entire feed forward net. And then at the end, we come back to the same output, 5 by 68, 5 by 68. But what we have is a much deeper and more robust representation of those tokens through this attention mechanism, through the feed forward neural nets. It's able to learn a more contextualized representation of those tokens, and these serve as input into the next encoder block, and you can have as many encoder blocks as you want. You know, 12 encoder blocks. And so this is the output of this is still the same. Output of this is just contextualized, deeper, richer representation of the tokens. And so now how does self-attention mechanism work? Self-attention mechanism works. For every token, we have a query, key, and a value. For every token is now going to have a query. Now this query is going to say what am I looking for, and it's going to attend in an encoder. It's going to attend to all of the other tokens, right, including itself. It's going to attend to all of the other tokens. What am I looking for in terms of the purpose? Right? Key is going to say this is the information. This is the information that I carry, and then value is okay. If you do select me, this is the information that I will provide. Now, these are the values I will provide. This is the information I provide. This is the information I carry. So key and value almost the same. Key is more. This is what this is what the information that is being carried, and value is the actual substance. Value is the actual substance. Value is the actual substance. Key you can think of as a summary of the substance showing what the token actually will carry what information. And when we do the dot product of QKT, right? QKT, and then we screw D, this is what this is going to give us, is it's going to give us similarity scores or attention scores between the current token and then every other token in the sequence, Then we do soft max over that, where we get how much attention. Now, how much attention should this token pay to all of the other tokens? How important are all of the other tokens in this encoder block, right? In this encoder block, and we can split this into different heads as well, but in this head or in this encoder block, if we don't have multi-head attention, how how much attention should this token give to other tokens? We have these probabilities, and then we take the weighted average of those probabilities by those value vectors, and then that's our representation then of that particular token. And we do that for all tokens. And these QKV matrices, so these are vectors, but these are ultimately multiplied by the original vector that we put in for the token, which is the positional embedding plus the right plus the embedding, right, times the weight matrix of Q, weight matrix of key, and weight matrix of value. Right, that's how we get to our QKV vectors for each token. And then after we have a contextualized representation, and then what do we do? What do we do after that? That's where our residual layer comes in. We add the new contextualized representation back to the input to this encoder block, which was the embedding. Right? Element wise, there's no concatenation. Element wise, we add it, and then after that we do layer norm. So within each representation, we take the mean standard deviation and normalize it within each standard deviation. This is different from when we do batch norm, right, which is across each feature dimension. This is independently across each token representation. Right, so it's not mean of the batch, it's not variance of the batch, it's mean of the token representation, variance of the token representation. Right, so each token representation mean is going to be different. After that, then we pass it to the feed-forward neural net, which it's going to take. Now, what did attention mechanism do? Attention mechanism, what it did is it tried to extract the meaning from other tokens and how much attention and value it should give to the other tokens and extract that. Now, feed-forward neural net, after you pass it through the attention mechanism, feed-forward neural net is going to create more enhanced representations of each of those tokens, right? So independently, right? Each token representation goes through the feed-forward net independently, and that is an encoder block. And then we have 12 of these encoder blocks. Now we also sometimes have multi-head attention, which is what the transformer paper used. We have multi-head attention, so instead of having just one QKV vectors, we split sometimes right into multi-heads. So in sometimes eight heads, and each of these have their own QKV vectors, at which then they do the attention across other tokens, and then we concatenate those. And why do we need different heads? Well, because each head then can focus on a different part of the sentence that it can extract of the sequence that it can extract meaning from the other token. So head one, for example, could pay more attention to, let's say, if something is a noun, to other nouns in the sentence, whereas head two can more focus on the direct words, whether they come before or after the token. So each head, depending on what it wants to focus on, can learn a different representation of the original to of the original token sequence. And so we have multiple heads in an encoder, and then we have many encoders as well. And that is our encoder. And now decoder, what the decoder is going to do is decoder uses cross attention. So we said that the decoder is only looks at the does not look masks the future tokens. Masks because it is useful for next token generation next because it is useful for next token generation. It cannot look at future tokens. Can't look at future tokens. So it's going to mask those future tokens, and it's only going to look at the 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 entire sequence up to that point which it has generated. And for cross attention, what it's going to do is it's going to take its query and it's going to compare to the keys and values or to keys and then take the weighted probability with the values to the output representation from the encoder. So this is crucial in, let's say, sequence sentence translation tasks. We're trying to translate a sentence to, let's say, English to French, right? And you have this English representation already built up through the encoder, and now you're trying to translate it. And as the decoder is trying to translate it outputs a certain token. Then it has to go back. Then it has to go back to the encoder representation and see, okay, which of these keys, right, align to this query that I have, So it uses its query, but then the keys and values from the encoder output. So that is what we call cross attention, where it's also using the encoder representation as well. And then that's decoder. That is decoder. Now, distribution shift is when our training data comes from a different probability distribution, from a different distribution entirely, from a different subset of the entire data set that we're creating our model from. And this does not reflect what the testing experiments and testing conditions will be. So one example is if you train data on, say, daytime images, let's say you're building an image classifier and you train on daytime images, and then your testing data, it's nighttime images. So the environment from which the distribution from which your testing data comes from is fundamentally different from where your training data came from. Pooling is when insurer says, okay, we don't want to pay these excess claims, and so we're going to set this pooling threshold, saying that, okay, after 800K, right, that's the threshold. We're gonna cut it off. But instead, what we're going to do is we're going to create this pooling charge that we're going to just redistribute to the other groups. So we have this threshold that we have, like 50,000, 80,000. We're not going to count as claim costs, right, that the insurer will pay out, but what we will do, we still have to account for those. So how are we going to account for those? Is we're going to convert those to a pooling charge that will then be redistributed to different groups. Retrospective versus prospective. Prospective is you're trying to create a rate using prior experience, and then you're going to use trend, you're going to use demographic changes, you're going to use health risk factors, you're going to use plan benefit changes to develop and create this rate for the future, for the next policy period. What retrospective is we have this baseline premium already that's set, and then that's what's going to flow through the entire policy period. And at the end of the policy period, then we'll look back and evaluate, did those exceed expectations or did those not? And if they did exceed expectations in terms of our claims experience was favorable, or was it not favorable? Or was it not favorable? And depending on that, we raise the premiums for the next, or we lower the premiums and do some sort of refund. CPD versus plan table. CPD versus plan table. Whenever you're trying to get the value of attachment points, use CPD instead of the plan table. ER multiple choice. We have favorable selection, right? Inertia, not knowing about these different plan provisions could influence their selection, mandating selection. So you have, if it's different plans within the same insurer, then use the selection load. But if it's different plans and different insurers, then you use the multiplicative factor with the relative health status. We know level funding, that level fund itself, which is the fixed premium, they go to ASO fees, IBNR specific stop loss premium, aggregate stop loss premium, risk classification, data quality, credibility, actuarial comms, all about report generation and identifying any model deviations you've made or any inaccuracies in the model that you found, any assumptions, credibility of the data quality, any errors, any missing values, any outliers, outlier detection, risk classification. You want to make sure it's reasonable, actuarially sound with proper judgment based on group characteristics.